So here we are, issue 317, and what's that now? 1,233 subscribers, and a wee bit of Googling going on here by the looks of it. And 12 squared and 33 squared makes 1233. More of that later, it says. Okay, looking down, Chris's Conundrums, that rings a bell. What's this? There's some imposter, a Mr. B, who's doing a mini-series where he outlines. Outlines. Sounds a numpty then. If you can only outline the solutions, you stick with me. Hopefully I'm a bit more thorough than that. Let's have a wee look down. Going down to this week's puzzle. Here it is. This week's puzzle. As I mentioned earlier, 12 squared plus 33 squared equals 1233. There is one other pair of two-digit numbers whose squares have this nifty property. Nae Googling, folks. Pot kettle springs to mind there. Given the information I've provided, a nice solution is possible. I want to see all your working. So here it is then. There's that pair. 12 squared and 33 squared is 1233. Now, it says that there's one other pair of numbers which have the same property. Can you find it? Well, actually, within this question, there's actually a whole can of worms waiting to be opened. There's also the problem of how would you have arrived at this one in the first place, and how do you know there's only one more pair that works out of all the possible two-digit numbers? Well, given that is the case, what could we say? If we call that number x and that number y, I'm looking for two pairs of two-digit numbers. Do they have to be two-digit? Well, certainly, to produce a four-digit number, x would have to be a two-digit number. And the least that x could be, because it'd have to take me into the thousands, is 10. So x is certainly greater than or equal to 10. The least that x can be is 10. Its square would be 100. To put it up into the thousands, that means that y squared would have to be 900. So y itself would be 30. So I've got y is greater than or equal to 30. But it could go all the way up to 99. Because even 99 squared is going to be, well, that's 100 take away 1, isn't it? So that's 10,000, take away twice the product, 9,800, add 1, 9,801. Adding on the 100 to that still keeps it under 10,000, in other words, still keeps it as 4 digits. So that could go all the way up to 99. So y is going to be greater than or equal to 30, less than or equal to 99. You've got all those numbers to try. Still, forgetting that, that's another question. Trying to find them in the first place. Given that that's a pair, can we find another pair? Well, if we're calling that x and y, now if x is a two-digit number and it's to occupy the first two places, that's going to be the hundreds and thousands. That'll have to be 100x that goes there. Then you can add on y, which occupies the tens and units. That would be the equation you would have, having to satisfy these conditions. Now, you're looking for solutions which are integers. So strictly speaking, you're taking this equation here and you're trying to solve it as a Diophantine equation. That simply means equations where you're only looking for integral solutions. Now, it is a quadratic, so you could think of it in two ways. It's actually something else, but more about that later. It is a quadratic. You could either consider that to be a quadratic in x. So if I rearrange that into a quadratic in x, I've got x squared minus 100x plus y squared minus the y, put wee aesthetic brackets around that to isolate the constant, equals 0. There's a quadratic in x, because obviously with two variables I can only find one at a time. But what this says is, for each value of y, there could be none, one, or two solutions, depending on what the discriminant of this is. So if I happen to know one value of y that works, that means there'll either be one or two values of x that will partner it. And up here I've got a pair. Here I've got y equals 33 is a solution to this equation. So if I put y equals 33 into this, I should get a quadratic that will provide me with one and hopefully two solutions. So I've got x squared minus 100x plus, now what's y squared minus y? Well, that's the same as y times y minus 1. So that's 33 times 32. Well, take the 3 in, 3 times that's 96, and then you do 11 times it, so adding that into the middle, that's a 96 with a 15 stuck in the middle, 1056, equals 0. Now you could use the quadratic formula, but you don't need to, because I can just factorise this, because I know one of the answers already. Instead of going through all the pairings of what numbers multiply to give 1056 and add to give 100, I can just say, well, I already know that 12 works. So 12 is going to be one of them. So what's the other partner? 12 times what? We'll just rearrange the factors here and you'll find it. You could just divide 12 into it, certainly, that may be quicker, but you could just rearrange the factors. If I take a 3 out of that one and a 4 out of that one, I'll have the 12. That'll leave an 11 and an 8, so that must be 12 times 88. And of course that works. 12 times 88 gives this, and 12 plus 88 gives the 100. This says the larger one is negative, this says they're both the same, so they're both negative. So there we are, x equals 12 or x equals 88. So that means the pairings are, if I put them together, I've got 12, 33, and I've got 88, 33. So this is the new one. This would say that 88 squared plus 33 squared should equal 8833, and it does. But what if we'd started with a quadratic in y? So what have I got? Y squared minus y plus x squared minus 100x, nice wee brackets around that, equals 0. Let's just box off these bits so we can see what's happening. Put that there and finish off that line here. Again, that's a quadratic in y. So for each value of x, there'll be a solution. Well, there'll either be no solutions, one solution, or two solutions for y. I've got some values of x. There's one to begin with there, 12. So if I put that into it, what happens? If I put x equals 12 into this, I'll have y squared minus y plus, and again, that's x times x minus 100. But that'll be 12 times negative 88, so it'll be minus 12 times 88 minus 1056 equals 0. Readily factorises, because I already had that product. Multiply to give 1056 and have a difference of 1. Well, they're 1 apart. Y 33, 32 equals 0. Make the larger one negative, make them opposite. So now I've got the solutions. Y equals 33 or y equals negative 32. Also know that 88 is a value for x. But 88 is going to give me the same solutions, because 88 will just be the symmetrical one to this, because I'll have an 88 times a negative 12, which is the same number here, so it'll give the same results. So this gives me a pairing here. This says for 12, I can have 33. So I had that already. For 12, I can have negative 32, but it also worked for the 88. So that was a 33. So for 88, I can have the 33. And for 88, I can have the negative 32. But I was only interested in the positive numbers, so that out of the 4 solutions, it was only these two that I wanted, the 1233 and the 8833. Notice these still work though, because they satisfy the equation. If you think of negative numbers going in for the digits that you used to have long ago when you didn't have calculators and you used to use logarithms to work things out, and you had bar numbers, so the numbers were made up of positive and negative parts. So you could say this should work. 12 squared plus negative 32 squared should give you 1, 2, but negative 32 as the answer. And, so what's that? That's 144 plus 1024, because that's just those powers of 2. So that should actually come to, that says 1178. 68. So how's that the same as that? Well, it is if you identify those negative numbers as having 32 missing from the units and tens. So that's like 1200 minus the 32, and if you take 32 away from the 1200, you do in fact get 1168. So that was only the positive one, so that's the answer. But now there's still the problem of, how would you get this one in the first place, and how do you know that there's only 2 and there aren't any more, or rather there's only 4 and there aren't any more? So, how do we do that? Well, you can just keep pressing the buttons until you find one that works, to find that first pair, that 12 and the 33. Or you could investigate the digits and see if that might shorten the search. There's still going to be some trial and error involved in it. So if I've got two two-digit numbers, if I make the digits in the first one AB and the digits in the second one CD, that means the first number, which I've called x, that x squared would really be a 10a plus a b squared. And that second number, the y squared, made up of digit CD, its actual value would be 10 lots of c plus d squared. And if the result of them is to form this 4-digit number, the value of that 4-digit number, so together they should form, that's in the thousands column, 1000a plus 100b plus 20c plus just d. Yes, that's just 10d. No idea why I wrote 20c unless I was just thinking twice the product. No, just expand. If I square and add these, what have I got? Square in the brackets. That's 100a squared plus twice the product, 20ab plus square the last, plus square the first, 100c squared, plus twice the product, 20cd, plus square the last. That should equal this. I could try and identify which parts of these produce numbers in those columns, but the problem is with large numbers, they spill over forwards. The only ones I can be certain of is the ones left at the end here. So that to produce this digit d at the end, which is in the units column, the only ones of these that could produce a digit in the units column, because these are all times 10s, notice, would be the b squared and the d squared. So that I know that if you add b squared and d squared together, they should leave a d in the units column. One way of saying that is they're congruent to d mod 10. Now I don't need to find them all. The way this problem works would be if I can just find one, if I can just find the easiest one, then you could use your formulas or something else to find the other ones. And the easiest probably just means what's the smallest one, the first one, the one most readily available. But unfortunately, to find numbers b and d that work for this, I still need to use a bit of searching. I'll need the squares of numbers to add them and find just one, the first one that works. So there's a list of the squares, one for b and one for d, or b squared and d squared, but I just need to find one. So this says if I add the two squares, the resulting number will end in the digit which produced the square of the last one. So just go through a couple. So if I try 1, in fact it can't work for any of those, so I'll switch to 4. 4 and 1 makes a 5, that's not a 1. 4 and 4 makes an 8, that's not a 2. 4 and 9 makes a 13, that is a 3, that would work. If you do 2 squared plus 3 squared, you get 13, which leaves a 3. So there's one pair. I've got b equals 2, d equals 3 for my number. So I could just put that in there, assuming it's going to work. So that's a 2 and that's a 3. There's other ones that could work, but I'm only interested in getting one of them. The other readily available one would be the very last one, as long as there was no spillover from the previous ones. Picking out the figure in the thousands column is okay, as long as none of the previous terms, spill into it. Well, the only terms that could spill into it would be these two here. The 20AB, I know it seems an awful lot of writing. You might think, oh, I've reached that number already, just pressing the buttons on the calculator till I found one. Plus 20CD. Now, taking the numbers b and d, that means that's 40a and 60d. No, c, not again. And even if a and d were their maximums, 9 and 9, 9 times that's just 360, 9 times that doesn't go to the 1000. So that means for b and d, it's safe just to identify now what might make this first one. So the first one must come from these two. So I've got this. I've got 100 lots of a squared plus 100 lots of c squared, so I'll just put that down as plus c squared, has to produce a number which has got an a, but not in the remainder position, in the leading position, which means if that number goes into the thousands column, if you divide it by 1000 and then take the integer value of it, that should give you the a. or cancelling that down, I want the integer value of a squared plus c squared to equal 10a. I'll just go through the numbers again. Well, just going through them. I've got 1 in there, it's just straight away. 1 and 9. 1 and 9 makes 10, and that is 10 times 1. So there you are. A equals 1, and c equals, the 9 means the c squared, c equals 3. So now I've got 1, 1, 3, 3, and that's my first pair. I just quickly check that works. 12 squared and 33 squared does in fact make that. So there it is. So I found it. Then I can use those equations to find the other ones. Or I could do something better than that. I could visualize it. Go back to that original equation. X squared plus y squared had to equal 100x plus y. Now, you can consider that as a quadratic in x, a quadratic in y, but look at the form of it as a quadratic in both of them. That's the equation of a circle. Just rearrange that a bit. X squared minus 100x plus y squared minus y equals 0. Complete the square, so half of that, x minus 50 squared, but then that would have a plus 50 squared, so put that 2,500 on the other side, plus y minus half of that, y minus a half squared, but that would add on plus a quarter, so put it on this side to balance it. No, just write it as a quarter. Probably better having that as 4 times that, it's 10,000, isn't it? 1001 over 4. That's the equation of a circle. There it is. Centred at 50 a half. And radius, well, the square root of that is just barely over 50. Radius just over the 50. So if I put the axis in, it'd be something like that. But there's symmetry in the circle. I know an answer. I know an answer to this. I know values of x and y that will do this, and that was 1233. 12 along, 33 up. Maybe that's not quite the right place. 1233 worked. And then from the symmetry in the circle, because there's an axis of symmetry at 50, which means that if this is 12 away from 50, which is 38 away from it, it'll be 38 away in the other side as well. So the symmetrical point would be 50 plus 38, which is 8833. And there's an axis of symmetry at y equals a half. It's not an integer, but it's not too bad in this case, because the distance there is going to be only 32 and a half, which makes it look as if it's going to go non-integral, but then 32 and a half on the other side of this takes you to negative 32. So 12 negative 32, and then by putting it across 38 gives the other point here, which is 88 negative 32. There's the 4 solutions just by considering symmetry in a circle. There's still the problem of, are there any more points that work? Because these are special points in a circle. These are the points in a circle where the coordinates are integers. They're known as the lattice points. And depending on the circle, it can have several or many or no lattice points. And that's the big can of worms here. This question really was just a special case of lattice points in a circle. That can get quite complicated. And if you did delve into that, you would find, if you understood it all, that this one, for this particular circle, there would in fact just be 4 lattice points. It is much simpler when the circle is centred on a lattice point and the radius squared of the circle is an integer. We'll do one example of that. So, not so much finding the lattice points themselves, because that would involve a search and then symmetry, but knowing how many lattice points there are in the first place is just as important, because if there's no lattice points, then there's no point trying to search for them. And if there were only like the 4 lattice points, then knowing one would give you the rest of them without having to then try and search any further, fruitlessly. One other thing here though is this little equation here. X squared and y squared is to make a number. Non-geometrically, geometrically that's a circle, non-geometrically that's just the problem of finding the sum of 2 squares. And there is a function called the sum of 2 squares function that tells you how many solutions there are to that. It would be written as R2 of n. And the result of that function would be, it would tell you how many pairs of squares there actually are that would satisfy that condition. Whether it's none at all or however many. It's a function, the sum of two squares function. Now, it gets quite involved. The first part of it is to write n as a product of its prime factors. Like this, where p and q are the two different categories of prime. Where p is a prime of the form 4k plus 3, and q is a prime of the form 4k plus 1. Now, those aren't formulas for a prime, because obviously, if k is 3, that's not a prime number. No, it's just that all primes must fall into one of those categories, simply because all numbers must fall into the category of they're either a multiple of 4, or there's a remainder of 1, or there's a remainder of 2, or there's a remainder of 3, can't write fast enough. They can't be primes because they're even, so all primes must fall into one of these two categories. Now, to actually evaluate this function to find how many pairs of squares there are, you have to do multiplications on these particular powers, this number of times and so on. I'm not going to do that because I found another short way for lattice points that short circuits this a little bit. The only thing to note here is that if any of these particular forms of primes, the 4k plus 3 primes, they all have to have even powers. If any one of those factors, those prime factors, has an odd power, then the result of that function is 0. So a useful thing to remember here is any odd power, any incidence of an odd power of one of the factors means that it'll not be possible to find two squares that add up to make the number. That's a handy one here. Still, I found another one for working out the lattice points in a circle, which is a simpler version of that sum of squares function, which is this. If I just do one in particular, well, if I've got this, I want a pair of numbers that add up. There's one that we know, 100. X squared plus y squared equals 100. How many solutions should there be to that? And this took the form of, write out all the factors. So it's 1 times 100, 2 times 50, 3 doesn't go in, 4 times 25, 5 times 20, 10 times 10, that's done because they're back the same now, I'll just be repeating them. You write out all the factors, and then you count up, so that you use a count. C1 stands for how many of these factors have got a remainder of 1 when you divide by 4. So obviously that's like the 4k plus 1 factors. So C1 is this. It would be count the divisors, D, such that D is congruent to 1 mod 4. So dividing by 4. That one does. That's remainder 1. That's remainder 1. 24. And that's remainder 1. C2 is count all the divisors, including the 1 and the 100, such that it's congruent to 3 mod 4. So you're counting up all the 4k plus 3 factors, if you like. Well, which ones have got a remainder of 3 amongst them? None of them. And then the formula for the number of lattice points on a circle is 4 times C1 minus C2. So in this case, it should be 4 times 3 minus 0, which is 12. This circle should have 12 lattice points. No fewer, no more. On this circle, there are 12 points where the coordinates are integers. There is, notice this circle's centred on the origin, but that could be for a circle centred at any point, any lattice point, because you could just translate it to the origin, find the lattice points, and then translate your answers back again. So centred at the origin, put in the axis here. So there's obvious symmetry here. If there's 12 of them, they'd have to be distributed equally. But not only is there symmetry between the 4 quadrants, with the interchange of coordinates, when you're looking for lattice points, you really only need to find them in one octant. Because about those two lines, y equals x and y equals negative x, if there's a lattice point on one side of it, there must be a corresponding lattice point reflected on the other side. So all I need to do here is find some simple ones, and then the circle will give me the rest. So x squared and y squared makes 100. Well, that's a perfect square. So 10 works, so I can get my trivial points. One of those could be a 10 and the other could be 0. That's like the points where they cut the axis. So those points are lattice points because this happens to be a perfect square. If that wasn't a perfect square, they wouldn't be lattice points. Also, if that's a perfect square, that means these intersections here can't be lattice points, because whatever the square root is, that distance would be, remember that right angle triangle, the 45 triangles 1, 1, root 2. If that was a 10, then these distances are 10 divided by root 2, which aren't integers. Although, if that was double a perfect square, so it was 2 times n squared, then they wouldn't be lattice points, but that would, because you'd have that, the square root of that, divided by root 2, which of course would be an integer. Still, that doesn't apply here. Now I just need one more. Well, that's an obvious one, because there's a 10. You think 10, you think right angled triangle with a 10 there. Well, 3, 4, 5, 6, 8, 10. There's one. So 6 and 8 work. So as soon as I put that in, as soon as I say 6 along, 8 up, immediately, with symmetry, I can fire in another 1 across to here, 1 down to here, 1 back down to here. There's another 4. Symmetry in the axis. Negative 6, 8, negative 6, negative 8, 6, negative 8. And then symmetry in the lines y equals x's, which just means interchange the coordinates. So 8, 6. 8, negative 6, negative 8, negative 6, and negative 8, positive 6. There's the 12 lattice points, and I know I don't need to look for any more because there's this little formula here, which was just a rearrangement of the sum of squares formula, told me so. All of this was opened up by that question, this big can of worms from a seemingly innocuous little thing about squares. I'll just stop there. You can wake up now